Welcome to Lecture 5. This is on the gambler's fallacy. Remember always to try to read the book first, and then my lectures cover the highlights, and then the video lecture goes over the highlights of the highlights. But it's no substitute for either of those, especially since those concepts and exercises will show up later on. Okay, so I'm not going to cover everything. I assume you've already read this as usual. I'll just hit the things that you need to know. So the first thing for chance setups, before we even get to the gambler's fallacy, we have to motivate that with some groundwork. Chance setups are basically basic models for thinking about and tuning intuitions about probability. And the easiest example is tossing a coin. Not an actual coin, but an idealized coin. The idea is if you flip a coin, every coin is slightly different, right? It might be weighted on one side slightly, not intentionally. There's a bit of thickness to it. So an idealized coin is infinitely thin. When you spin it, it has regular rotation. And the idea is that you don't know if it's going to come up heads or tails, but there's a 50-50 chance, exactly 50-50. And from that, we can start thinking about what does it mean to talk about 50-50 and all the rest. So the first thing we're going to talk about is the notion of unbiased. Unbiased in regular language, in everyday ideas, is the idea that, look, you don't have any prejudice against a person or belief or whatnot. It's hard to imagine that being completely true, since as human beings we often have various sorts of preconceptions, conscious and very often unconscious. But ideally speaking, an unbiased situation is one where you have no preconceived ideas and you judge the situation as it is, right? In this case, what does it mean to have an unbiased coin? Well, if the coin is truly unbiased, then that means it is equally likely to come up heads as tails. If the coin and you toss it not just 100 times, a million times, a billion times, but forever, if you found that on average it showed up more heads than tails, then you wouldn't claim the coin is biased. You wouldn't claim it's unbiased. You would claim that the coin is biased. And that's the idea behind the notion of unbiased. It's about the frequency, relative frequency of outcomes in the long run. So in this case, think of the coin, you toss it not just once or twice, that's not going to be enough to show you. Even 100 times, you got to toss it an infinite number of times to show its true nature. And you can think of that commonsensically like in the world. A person's true nature, character, is shown over time. Not once or twice, but what they do in the long run. And that's hard to see. People often are judged on the basis of superficial things, not long run type activities. Okay, the other major definition is independence. Independence is the idea that when you toss a coin, it has no relation. It's related to bias, but it's not the same. It's no relation. Independence is the idea that if I toss a coin once, I pick it up and I toss it again, the previous toss has no effect on, no influence on the second toss. Each toss is independent of the previous tosses. Words that describe the notion of independence: randomness, no regularity, but the one I'm going to use probably most often is no memory. Each toss has no previous memory built in, right? Every toss is fresh and new. This is a really important idea. It's also philosophically very difficult, but we're going to not really dwell on that in this course. Okay, putting those two things together, you say a chance setup is fair if, that's a fancy way of saying if and only if, which is another way of saying equivalent to, it's first off unbiased, and two, each outcome is independent. So what it means to be fair is first off that the coin, if you toss it in the long run, will show up 50-50 heads or tails, right? So that's the notion of unbiased. You wouldn't claim a coin is fair. Suppose you got two teams and they're tossing a coin and it's weighted. The team that calls it, knowing which side it's weighted, has an advantage, so it wouldn't be fair to them, right? Fair means fair for both sides. So first off, it has to be unbiased. But secondly, you also need each outcome to be independent, because if there's memory built into the system, say of coin tosses, then if one team knows what the previous coin toss was, they'll know the next outcome. So independence is also required. As a side note here, one example of how this is violated in Vegas, when you play the slot machines, it looks like those things are independent. In fact, every toss you make, every pull of the lever you take, has a computer program running an algorithm that's using what's called a random number generator. And it makes it seem as if each toss, in this case each spin, is independent of the previous ones. In fact, the computer predetermines exactly where it's going to go. And if you know the code, you can win big. You can also get arrested. And given that it's Vegas and it was founded by the mob, you can get much worse. Okay, moving on. Now we have the pieces to talk about the gambler's fallacy. A fallacy is the idea of something being incorrect but psychologically persuasive. Fallacies are really important in logic, and we'll talk a little bit more about them later in the course. But the notion of fallacy is that this thing looks persuasive, the mind has a tendency to go this way, but it's incorrect. So to use a concrete example, let's talk about a roulette wheel. If you guys go to Vegas, or even if you don't know anything about gambling, you know that spinning wheel, you toss the ball on it. It's sort of like tossing a coin because it's roughly 50-50. There's red and black, and you can bet either way, right? It's not exactly 50-50 because there's some other slots. But the point is, you throw the ball on the wheel, the wheel's spinning, the ball bounces around, hits one of those things. You can bet on red and black. Gambler's fallacy says that after you see a run of certain things, you're inclined to infer in another way, and that it turns out that's not correct. So, without you can read the rest of the lecture, but let me just use that example. So, if I see a run of 12, let's say blacks on the roulette wheel, I'm standing on the side, and I see people bet, and I see it come up black once, and then twice, and then three, 12 times in a row. I'm thinking, man, that's unlikely. 12 times in a row. The next one, the wheel has got to go red. So on the 13th, I finally go in there on the wheel and I say, I'm going to bet all my money on that 13th toss being red because it's got to go the other way. That's the fallacy. You think that basically it has to go that way. Where's the fallacy? Well, first off, assuming the wheel is fair, meaning it's unbiased one and each roll, in this case, each roll of the ball, is independent of the previous ones. The long run outcome, the wheel may be unbiased, but where the fallacy occurs is in your inference that there's a memory to the wheel, so that on the 13th spin, on the 13th toss of the ball, it's going to have a memory where it says the wheel thinks, I've gone 12 times hitting black. The next one I got to even it out, so I'm going to go red the next one. The wheel doesn't do that. The probability of getting a red on that 13th spin is the same as the previous one. So whether you go black or red doesn't make any difference. It's still 50-50, roughly speaking. Okay, that's it for the lecture. Um, what I recommend doing is working, as always, the exercises at the end of each chapter. You don't have to do them all, you do some, but there's a few in particular that will help you for the upcoming quiz, and I'll give you some guidance there when you open up the quiz file. As always, try things on your own and then use this extra guidance to help solidify your understanding. Using this as a substitute for understanding, you will pay the price in the longer run. Trust me on this. So just do the work in good faith and you should be fine. Okay, see you next time.